Buenos días, estamos por arrancar el webinar. Tengo en la línea a Mike Engelhardt, que él es nuestro experto dentro de Corvo, responsable de todo el desarrollo que se tiene para la parte de Spice, en este caso QSPICE. Y también está Tim McCune, que es parte del equipo y así que responsable de que todo esto esté funcionando de mejor forma. Entonces, vamos arrancando. El webinar va a estar en inglés. Mike, when you're ready, let's go and move on. The session will be recorded, so we are going to be able to share the information later with the attendees and also the details of the training that it will be really, really helpful. Everything will be good as well for the implementation that you will be able to access. Also, the QSPICE from the website is completely free. I will put on the texting area and the chat box a link so you can get it online as well. Okay, we're ready to go.
All right.
Go ahead, Mike.
Thank you very much, Gerardo. So I am going to share screen here. All right,
I'm sorry.
QSPICE.
I forgot just to mention there is a section for questions and Q&A that please feel free to do the questions. I will be able to read the questions back to Mike in case you want to, in the middle of the presentation, have a question. We can address immediately in that moment. Go ahead, Mike, sorry.
Yes, of course. Yes, you do feel free to interrupt with questions. It actually makes the whole thing more. It works a lot better if you do that way because I can't see your faces, and so I'm just talking into a dead microphone as far as I know, and only if I get questions can I get a better read on whether or not I'm talking clearly. So I'm the person that wrote QSPICE, and QSPICE is a general purpose circuit simulator with phenomenal mixed mode simulation capability. It's not the first simulator I've written, though. And so it's probably worth thinking a little bit about why you would write another SPICE program. And basically, it comes down to this. And Berkeley SPICE, all these SPICE programs are based on an academic code called Berkeley SPICE that was written many decades ago. And it is a very difficult code. Even if you've had someone from the UC Berkeley original CAD group explain it to you and explain why it's written the way it is, which is, it amounts to the fact it was written in a form of object-oriented programming in C way before C++, and it's very obtuse, and it was just a coding style that died on the vine. You can't understand it if you just walk into it with a normal software background. You need someone from the group to explain it to you. But even if you've had that experience, it's still hard to work on because the nature of the way it's implemented. Now, other things that have changed is that computer hardware has changed, and this means that you'd want to write your algorithms in a different method than what you would have written because, for example, computers now can compute faster than they can look up. That is to say that it used to be the fastest way to compute something was to not compute it at all, but to get it out of a lookup table. Well, today that's very often the worst thing you could possibly do because for example, say the amount of time it takes to do a floating point operation, multiply two 64-bit double precision numbers to a 64-bit accurate result. That doesn't take one clock cycle. Each clock cycle is, a couple hundred picoseconds because for a 5 gigahertz processor, it's 200 picoseconds. It doesn't take one clock cycle. Today, it takes 3. There's only 3 latent clock cycles at the end of the pipeline in the floating point unit to multiply two 64-bit numbers to a 64-bit accurate result in floating point. And that means that you can do it in a small fraction of a nanosecond. But if you try to get that up out of a lookup table, where you have to go to the pin drivers, you have to go through the copper traces, you have to go into your DIMMs, and then you have to go through on almost another computer on the DIMM sets to get to the actual RAM. All of that takes, at least 60 nanoseconds. So computers can compute faster than they can look up, and that changes the algorithms that you use. Also, Numerical methods, the methods used to compute something. This is a new field, and it has changed a lot in the 50 years that numerical methods has been around. The original numerical method, the term didn't exist before the fast Fourier transform, popularized by Turkey and Cooley in 1965. And the thing about that algorithm was that it wasn't just faster, it was also more accurate. So there was like a whole field out there of how to compute things faster and more accurately than what one would originally think would be a method of computing that. So those new methods that are known today. But this is another really big thing that no matter what, besides all the technical stuff, I mean, these simulators have been around for decades and we've used them for decades, and we actually accomplished something. We're not designing the same circuits anymore. Today, we're simulating different circuits. So basically, what's happened is that what you have to simulate has changed. Simulation requirements have changed. And one way in which it has changed profoundly is the amount of digital logic that is in any circuit that you do today. I mean, it was great a long time ago when you could just be an analog engineer. And, because analog engineering, analog electronics, it's just beautiful. It's interesting. It's beautiful. It's something that isn't taught in school. So you have to go learn how to do it yourself. And it was a good living. But today, everything has digital logic in it, and probably even massive amounts of digital logic. In fact, we're actually kind of at a point where if you can't digitize the result, you could wonder whether or not it's real because you can't archive it, you can't communicate it to someone else. You have to be able to digitize anything you do. So that's why you'd write another simulation program. This slide just gets into some of the details, but I think we don't need to talk about this. There's one thing here which is kind of interesting. So for entertainment purposes, I'll explain this thing about Laplacians. It's the ability to analog simulators have long had the ability to simulate a component described behaviorally in the frequency domain. The technique is to give the Laplacian equation for that device. Laplacian equation is describing it in the frequency domain in a variable called S, and S is 2 pi times the frequency times the square root of -1. That's the Laplacian variable S. And so you'd love to be able to describe things in the frequency domain because that is often known. That is often what you're thinking about. And then you would like to know how it looks in the time domain, which would be a very valuable thing to be able to compute. But here you instantly run into a fairly difficult problem. If you know something in the frequency domain, if you know the behavior in the frequency domain and you want to describe it in the time domain, the only method that works for a general expression expressed in the frequency domain is to do the Fourier transform of the frequency domain response. And that gives you the impulse response because you know that the Fourier transform of a delta function is a flat line in frequency, all frequencies equally considered. So if you take the way your behavioral part colors that flat response and do the FFT, you get what the impulse response you get what comes out from an impulse response. And then you convolute that impulse response with the actual waveform in the time domain that you apply to the input of your transfer function. So, that's a simple idea. What could possibly go wrong? And the problem is that you basically can't do that from because it's basically instantly compute bound. Just getting the impulse response is problematic. Usually you can do it, but there's a problem just in that step because you'd like to use a faster routine like an FFT to get the impulse response. But the problem is that you need to look at very many decades of frequency. So you'd like an FFT that lets you have frequency bins that are spaced exponentially in time, so that each bin further out is a bigger swath of frequency, and no such routine exists. All you can do is try to pick the decades of interest, and then maybe do an FFT of 1,000,000 points. Capture 6 of those decades and do the Fourier transform of that. That is that often doesn't work, and even if you get that. Now you have a impulse response with 1,000,000 data points. And for every single time step you want to consider, you have to convolute those 1,000,000 time points with a tiny sliver of the impulse response. And that is so compute bound, you simply cannot do it. It is not possible. And so what is done is very many approximations are used. So after you've done the 1,000,000 point FFT, you compress that in a lossy compression scheme to get something that looks about like that, and then you use different methods of trying to integrate, convolute the actual response with this impulse response, and that is that there's so many approximations you have to do. The net result of the industry is that if you put the same Laplacian into 3 different simulators, you will get 3 different time domain response from that. And in QSPICE, I was just tired of the situation, so I don't do that at all. Instead, I synthesized a circuit from the Laplacian. And basically, if you have a Laplacian expressed as a ratio of polynomials in S, which is the nature of most people who study Laplacians, that's the format. It's a ratio of polynomials in S. And if you have a ratio of polynomials in S, you can robotically, like a robot can synthesize a circuit with capacitors and transconductances that has exactly that frequency response. And if you do that, then use that circuit for the time domain response. 2 things happens. One is that it is exact. It's not an approximation. That is exactly the frequency domain. That is exactly the time domain response. That's one thing that happens. The other thing that happens is it's exceedingly fast. It'll be the fastest thing in your circuit. So that's one of the new methods that's in QSPICE is synthesize the circuit. There's a downside to this in that it won't work for a general routine. You have to be able to express your Laplacian as a ratio of polynomials in S. That's the limitation of it. That's the nature of most Laplacian work. And if you don't express it that way, it will try to symbolically reduce your expression to that. But it's kind of a crude routine I wrote myself. But anyway, those are the difference as far as hardware and software numerical methods. Okay, so what QSPICE is, there's 3 aspects to QSPICE that make it compelling. One is that it's just a better SPICE program. If all you want to do is analog, it's a better SPICE program than you've seen before. To do that, I removed all the device IV curve discontinuities. So there's a lot of bugs in Berkeley SPICE. The IV curves that have discontinuities in them, and these discontinuities cause convergence problems. That gives you better transistor level simulation. And I re-architected the time step control entirely so that it just simulates. It takes smarter time steps so that it gives you a more accurate answer quicker. And it's extended to new device types. Wide bandgap devices are native circuit elements. There were legacy devices that had incorrect device equations. I've corrected all of those. The net result is that it's the most robust and correct SPICE I've ever seen in my life. That's one thing that makes QSPICE compelling. Just better, basic, old-fashioned SPICE basics. Now, another thing about QSPICE, I've mentioned this already, about the mixed mode simulation. QSPICE has flat-out phenomenal mixed mode simulation performance. The way it gets that is that it takes your it can take your source code like Verilog or C++. It will compile the Verilog or C++ to native Intel object code, and then it executes that object code to evaluate your digital logic. The compilers to do all that are included in QSPICE. The net result is that digital logic evaluates faster in QSPICE than it does in hardware. In fact, it actually simulates digital logic better than most dedicated digital simulators. It doesn't have the debugging capability, but if you just want to present a massive amount of digital logic to your SPICE program, this is the way you would do it. And it's very I try to make it extremely accessible to you. All you have to do is draw a symbol, type in some source code, and run, and it will compile the code and take care of all the details for you. So this is what I mean by removing discontinuities. if you curve trace a MOSFET in Berkeley SPICE and get it into channel punch through, the IV curves from Berkeley SPICE look like this. And this is just a bug in the program. See, this discontinuity is an error. The transistor doesn't behave like that. In fact, this line should be extended on top of that line. This line should be extended, go off that. So it's a bug in Berkeley SPICE. And the reason why a bug like this can exist for decades without anyone complaining about it is that it's actually not a circuit problem. This is channel punch through, and good engineers do not punch through their channels. So you never see this in a board level circuit. But it's a big problem for simulation because the simulator doesn't know you're not punching through your channels. It has to solve that you're not punching through your channels, and it iterates the solution of your whole circuit. And if it ever, by chance, gets to this part of the circuit, it cannot analytically iterate over to the correct point. And you get a convergence problems, which you can't understand unless you single step through the whole simulation in a debugger. Anyway, all that stuff is gone in QSPICE. Here's another example of a different discontinuity, different simulator, and that's fixed in QSPICE also. So that's what I mean by removing device IV curve discontinuities and fixing old bugs in Berkeley SPICE. Now, this is what I mean by correcting legacy devices. And this is for a JFET. It applies to other transistors too, but JFET would be the most clear example of the equations in SPICE simply being incorrect. If you curve trace a JFET in Berkeley SPICE or PSPICE or HSPICE, you go plunk down $100,000 for Spectre. These are the IV curves you will get for that JFET. Okay. But that's not the way a JFET actually works. If you actually go curve trace a JFET, they look like this. Kind of looks a little bit more realistic. And you cannot get these curves out of a normal simulator. And in QSPICE, this is all fixed. You can make a JFET that will actually behave like you can actually the device equations in QSPICE are extended so that you can actually encapsulate the behavior of a real practical JFET. Again, the reason why a problem like this, an error like this, can exist in SPICE for so long is that JFETs are always kind of second-class citizens to SPICE users because SPICE was for IC design, and ICs are made with MOSFETs, not JFETs. You can put some JFETs on it, but everybody accepts a huge production scatter. So the fact that the model was incorrect didn't affect too many people. Though a lot of that design flow was because the simulator couldn't simulate a JFET in the first place. So that's what I mean by just correcting device equations. Okay, this is what I mean by correcting time step. If you put a sine wave in Berkeley SPICE, you can get a waveform like this. Every single data point is exactly the right data point, but there's not enough data points to actually look like a sine wave. And in QSPICE, that's fixed. QSPICE will actually knows how to solve for the number of data points at each point in the sine wave, so that if you linearly interpolate between data points that are printed to disk, every single point along this line is within your specified tolerance, which defaults to 0.1%. So if you say you want 0.1%, put in a sine wave and do an FFT to look at the noise floor, your spurs will be 60 dB down. If you say 0.01%, they'll be 80 dB down. QSPICE just solves that problem for all the different sources: sine waves, single frequency FM, exponential, decaying exponentials. It knows how to solve that. It knows what time steps to use. Here's another aspect of time step control. Okay, this circuit here is something that you can put in Berkeley SPICE. It is a capacitor charged with a current, and there's a switch. The switch is hysteretic. Once the voltage on the capacitor gets too high, the switch closes, it discharges, and once it's discharged enough, the switch will go open circuit. So this is a way of making an oscillator. And so you would expect this on this node to see a sine wave or a triangular wave. But if you put this in Berkeley SPICE, the triangular wave is very chaotic, and the mistake that it's making is that it's confusing time step iteration with the Newton iteration for solving the nonlinear circuit. The way this has survived for so long in SPICE programs is for two reasons. One is that when I talked about eliminating device IV curve discontinuity so that you could analytically iterate to the solution, a core part of the SPICE algorithm is it relies on continuous IV curves, and a hysteretic switch doesn't have continuous IV curves. So people kind of tolerate that it's outside of the scope of what the solver is trying to do. And besides, if you stipulate a very small time step, this waveform cleans up. It looks more like a triangular wave. But that's not really good enough. There's no reason to accept that. If you don't confuse Newton iteration and time step iteration, then you can solve this thing. You can solve this thing perfectly correctly. And this is actually the basis of the mixed mode simulation in QSPICE. Digital logic doesn't have continuous IV curves. They're discontinuous. There's no derivative to the behavior of the inputs. The output is independent of the inputs, but QSPICE can just solve this larger physical problem. It does it optimally. So that's what I mean by re-architecting time step control. Okay, if you just do that to your SPICE program, what you end up with is a much better SPICE program. And these circuits, these are netlists collected in academia that were used to measure the performance of one SPICE program after another. They find they find various discontinuities, they find various errors in the implementation, and it's very hard to run these circuits. I did not collect these circuits. This is not a benchmark I collected. It was made by other people in academia. And what I've done here is I've run these different netlists in QSPICE and a couple of other very popular SPICE programs. And there's two things you want to look at. One is whether or not it can solve the circuits, and then second, whether or not it can solve it fast. Well, here if you add up the number of failures, QSPICE has 0 failures on all these circuits. I've never in my life seen a SPICE program that can run this entire benchmark suite collected in academia. This is the very first time I've ever seen that. Also, then in calculating the number of times it's in first place, it's usually faster too. It's easy to measure. The QSPICE is the fastest simulator. All right, continuing. There's one last thing that makes QSPICE compelling, and that is it uses the GPU. It uses the GPU not for simulation, which is a bad idea because the GPU doesn't have extended precision like a CPU does, but it uses it for the graphics, and that's a very big deal. SPICE programs make so much data, you can't plot it on a normal PC. You have to compress the waveform data so that you have less data, and then you can plot that. Well, if you use the GPU, you don't have that problem because the GPU can plot lines 100,000 times faster than a CPU can. Waveform compression is going to give you typically a factor of 40-fold, not 100,000-fold. So you don't have to compress the waveform data. You can just plot the data. And that's a big deal. You can plot every single time step faster than you could do before. And for the first time, you can actually see exactly what the simulator is doing. You can criticize every time step because you get to see them all. The waveform compression is sometimes used in SPICE programs to obscure what it's done so you can't see. You couldn't actually solve things. It just wouldn't plot the hard parts, so it didn't look right. The other thing that GPU does is that not only does it draw faster, it does dithered lines so that you never see a pixel. It will adjust the density of pixels adjacent along the line, so it looks like you painted it with a paintbrush instead of on a computer screen. It's a fairly subtle effect on a 4K monitor, but once you see it, you just can't go back. You just can't go back to these an older CAD tool that looks like you're actually trying to draw your schematics on a 1970s Pong game with where you can see every pixel. The result is that every single thing you plot or draw in QSPICE is always desktop publishing quality. So those are the three things that make QSPICE compelling: better SPICE basics, phenomenal mixed mode simulation capability, permanent desktop publishing quality graphics that's fantastically faster than what you've seen before. Okay, now other things about QSPICE is that the user interface is updated. There's almost no modal dialogues. See, a modal dialogue is these pop-up dialogues. So normally in an electronic CAD tool, you place a resistor and then you right-click or double-click on the value and some dialogue pops up. You enter the information in the dialogue, you say okay, and then you have to move your eyes back to the resistor. Well, the problem with that is, these pop-up dialogues are no fun. You have to move your eyes around the screen. You're looking at one thing, and you'd like to just leave your eyes rest at the thing that you're editing, edit it there, and then continue. And that's the way QSPICE works. When you put let me show you what I mean here. So here is a component. Say if I put a resistor, I just double-click on this, and I enter what value I want. All right. So I don't have to. The point is, I don't have to move my eyes around the screen. If you're 30 years old, you probably don't care. But as you get older, it's not fun to have your eyes dart around the screen all the time. And if you get used to this, you'll realize that your blood pressure is definitely lower editing things in QSPICE because you don't have these pop-up dialogues irritating you all the time. You can rotate things by 45-degree increments here. So if you want to put a diode at an angle, that's fine. And all the editors work in place and at these editors. These are not Windows editors. This is all part of a QSPICE GUI implementation. The user. Okay, one thing about QSPICE is that the symbols are stored in a schematic, so that if you make your own symbols and use them in a schematic, and then you email the schematic to a coworker, he has everything he needs to open up the schematic. All the symbols are in the schematic. The only reason for having a schematic file is so you can import them into your schematic one at a time. Like if you look over here, here's the symbol browser. If you want to put a deflop here, this deflop is not in the schematic, but now it's part of the schematic file because I put that deflop on the schematic. Okay. Oh, and one other thing is that you can document how the board might be stuffed. You can say, right-click, don't stuff. It'll just it'll give you a little ghost pattern of thing, or you can say it's stuffed with a jumper. And in fact, you can just use the semicolon key to comment stuff out. So that's makes it a little easier to document your schematics. Now, one other thing about the user interface is the selection guides are updated. Here's what I mean by that. Say you have a varactor, you right-click. This book with a little balloon symbol is the selection guide, and it will tell you, you can look at the part number of the varactor, who made the thing, what the zero bias capacitance is. You can click on headings and sort them. And it will show you the grading coefficient. The grading coefficient is the measure of how fast the capacitance change with bias voltage. So that is, it has pertinent selection guides for different devices. So you can sort them by the quality factor, the loss, the non-lossless of the varactor. You can sort it by all these different criteria. For a MOSFET is where you see it really starts getting valuable. So in MOSFETs, you'd like to be able to sort them by RDS on. Okay, but these RDS-ons are basically the rating from the datasheet of that part, and some MOSFETs are intended to be logic level, and some are intended to use with a much higher gate voltage. But to be fair, you should probably sort them by the way the FET is meant to be used. But say you know what gate voltage you want, you can say what gate voltage you're interested in, say 4.8 volts. And it will compute the RDS on for all those devices. And you see some are infinite. So what I'm saying is that you get the selection guides are smart enough. You can say what voltage you want to run the thing at. It will show you it will be able to compute the RDS on for that FET at that gate voltage. And that comes into JFETs too, because JFETs are usually run with when you fully turn on a JFET, you have you usually have zero gate source voltage, and you can sort them by RDS on. But if you have a wide bandgap JFET, Well, actually, any JFET. If you forward bias the junction on a JFET, it costs you some current, but its gain keeps increasing. If you've got the current, it's got the GM, and now they usually run at 0. But with in making nuclear instrumentation, I put as much as a few hundred microamps into a JFET to get more gain. But in silicon carbide JFETs, you can put 2 volts forward, and you still only have a picoamp of current. So let's put 2 volts forward here, and here you can see that this JFET has it's a 750 volt JFET and a 4.3 milliohm on resistance. So these selection guides will give you a fair bit of information about the different devices. Here for Zener diode is another example. You could, it will plot them by the Zener impedance and not only Zener voltage, but you get to know the Zener impedance of the thing. For standard devices, the selection guide is a matter of standard values. So here's all the percent values. These are, the technical term for these are called E96 because it takes nominally 96 values to have a percent changes from over a decade. But you can look at the 5% values, and those are listed for the E12, where it only takes 12 values to go from to span a decade. So it has just better selection guides. Okay. Now, other things about QSPICE and the user interface is that it's easier to overlay data. And there's a bit of a story here. People that come from a SPICE background know that the way to overlay simulation data is with this obscure command called .step. I mean, you have to learn that SPICE does this with .step. You have to have your circuit. You make a component with a value parameterized by some user-defined parameter, and then you step that parameter. So you need to learn how to use .step. There's nice things about using .step. All the simulation data, every simulation is in the same address space, so you can plot it and you get to know what values were used for each step. It has advantages, but it's not what, if you hadn't come from a SPICE program, it's not what you would have wanted. Now, other people from other simulators don't tend to use .step. They just overlay simulation results. And that's wildly more flexible. It has its downside. You might have 2 circuits with 2 voltages called V out. Now you can overlay them, but there might be V outs from entirely different circuits, and they have the same label, and it's up to you to know which V out goes with which data trace. But anyway, QSPICE allows both, and that's quite useful. Let me give you an example of doing that. So here is a circuit from my favorite professor in northern Germany. He sends me all these problems, and he says, "Okay, this is my crystal, and I'm going to simulate this, and that's my waveform. But I've actually measured this thing, with some Roden-Schwarz instrumentation. So I want to overlay my measurement on my model to see if it works. And here, someplace I should have this. Where is? Okay, here we are. Okay, good. This file here. This file looks like an Excel file. Here, let's it's an Excel CVS file. Okay, frequency measured. It gives you all these numbers. We can just take that CSV file and drag it onto the plot and overlay the data. So it's got drag and drop for overlay data. You can overlay as many waveforms as you want. There's a little here under file overlay. See, you can export the data. This data going up, data coming in is overlay simulation. There's a little tool that lets you manage which files you're going to overlay. And oh yeah, one other thing I should say. Let's overlay that again. What did I do with it? Here it is. If you add a waveform trace, now you have this thing about you're going to plot expressions, but you can plot expressions of from all the different. Let's plot that V measured squared. So the waveform editor here, the thing that lets you compose expressions of waveform data is more complicated. You have to say which waveform you're referring to. Okay. So that is that's really useful. I use it a lot when curve tracing waveforms and then change, getting either making models or correcting device equations so that actually so the simulator can work like the real part. QSPICE is kind of a thing at this point. It won Design Tool and Development Software Product of the Year. So it's real. It's out there. Now this addresses something that is important to you, but it's actually it communicates to other semiconductor manufacturers, but it has a lot of importance for you. Here's the thing. When you get a SPICE program free from a semiconductor manufacturer, whether it's LT SPICE from ADI or TINA TI from Texas Instruments, they'll give you this thing. It's free. Oh, but you can only use it for simulating our parts. Otherwise, it's not free, and it may not even work. So if for example, if you look at the LT SPICE license agreement, other semiconductor manufacturers are prohibited from authoring models for LT SPICE and promoting their products with LT SPICE. If it's a semiconductor manufacturer that doesn't make integrated circuits, they don't care, as that's just the way things have been. But if you're making if you're making switchers and you author LT SPICE models, then our ADI's legal department will lovingly reach out to you and let you know how the agreement reads and put a stop to that quick. QSPICE doesn't work like that at all. QSPICE is free for everyone. Um, Texas Instruments is welcome to standardize on QSPICE, and they should, because it works so much better than anything else they have. It has much better mixed mode simulation. It's much easier to make models in QSPICE than it is in any other simulator. I have authored, you probably know I wrote LT SPICE. I actually made the majority of the models in LT SPICE, and I know what goes into making those things. And I actually wrote QSPICE to solve that problem so that one individual can make all of the models necessary for some S&P 500 semiconductor manufacturer. So everyone should eventually standardize on this. It makes them, they don't quite understand that it actually is free and always will be. But QSPICE is, everyone is willing to, everyone is welcome to standardize on QSPICE, even if you're a competitor making parts that can compete with Qorvo or products that Qorvo in the future will provide or offer.
Hey, Mike,
okay.
there's
Yes.
a question I know that you are going to answer later, but just to keep in mind, they are asking something about what happened when the models has a transistor inside of in a sub-circuit. So that I know that it's in the backwards, but just to keep in mind to respond that question.
I'll when you make a sub-circuit, usually the models necessary for transistors are inside the sub-circuit. So that problem is if the model is implemented as these things normally are, that's usually not a problem. I will show how to import third-party models. I'll say a couple of words about it now because it's so important. It really doesn't matter which simulator you have. You're not going to have models in the simulator for everything you need. If it does, then you're simulating an old circuit that isn't interesting anymore. If you're doing anything leading edge, you don't have models for what you're simulating. So what's important is to be able to import models easily. And just like you can drag and drop measured data into a waveform viewer, you can drag and drop models into a schematic, and then it'll make a symbol for that model, and you can simulate with it. And I will demo that in some detail later. Okay. Is there some aspect of that question I missed that I should address now?
Luis Perez, can you please confirm it was answered the question?
See, this is where it's a lot easier to do this in person, because if it's in person, I know when to stop talking, because if the person who asked the question, once he's smiling, I can stop talking. But if he's not smiling, I haven't answered the question. I can't tell, sitting here talking into a dead mic.
Yeah.
All right, I made him shy, maybe.
Phone is partially answered.
Partially answered, I see. That doesn't sound like a smile to me. What else do I need to tell him? What else does he need to know, please?
1 second, I'm reading. It's okay to continue, and we engage with you when you are putting like the importation of the models. I think that will be better, easier to explain with the demo that you are doing.
Well, that's a very gracious response. I will continue. Thank you. I'm going to show a few examples. The first one is a curve tracer. This is kind of important to me because this is one of the times when I've used it. I curve trace transistors, and this thing, if you're going to curve trace a power transistor, you have to pulse the signals. You can't just use a DC curve tracer. And I was originally going to use, a PCIe card at a desktop and write the pulser in software and have a minimum amount of hardware for this tracer. But when I got further down that line, I looked at the cable that goes from a PCIe card. The cable alone is like $200, and then you have to cut it, and then you have all these itty tiny wires in there. And I would have to have a desktop computer in my lab to do this. And that wasn't very attractive. So I decided instead to use a USB little converter block that was powered off the USB. And because the nice thing about those is that they didn't have a cable connector. They had these little turn screws. You stick your own cable in and turn down the screw. And that just seemed like a lot easier to work with. The disadvantage of that is the USB is working on basically DC. And so you have to put your own time base and sampling holes for the signal for the converter. Well, so this is the circuit I use. Here's the sampling holes. Off the shelf worked fine for those. And to convert a DC level into a precision pulse, the normal way of doing that is a JFET and an op amp. You put the JFET into the virtual ground of a transimpedance amplifier, and you add a resistor in series with the JFET. So the JFET's already on, basically is not a critical part of the circuit. So in this circuit, if this JFET is on, then it's an inverter. It's a -1 inverter. If this JFET is off, it's a voltage follower, and the voltage on the output would just be the voltage on this node. So this node is usually ground. So let's ground this node and show the normal operation. The way these things are usually made, these JFET pulsers. And that's the pulse coming out of this thing. Let's zoom in on one of these pulses. Okay, so the problem is that these spikes here is charge injection. The JFET has capacitance, and the transimpedance amplifier is acting like a charge-sensitive amp, taking the injected charge and turning it into an output signal. So this spike and this spike you don't want. That's bad. So in this circuit, I used QSPICE to design a circuit to get rid of those spikes. Basically, on this node, instead of connecting it to ground, I mock up the same circuit on that. So if this JFET is on, this node is ground. If the JFET is off, it's still ground because it's connected to ground through here instead of through both of them. And then the charge injected cancels. So this is what the pulse looks like. So I get a perfectly clean pulse with canceled charge injection. That's just one of the uses I've used for QSPICE. That's mostly just using its analog capability, though these ICs were done as mixed mode simulators, using the mixed mode simulation capability. That's why it runs so fast. I think 1.5 seconds to simulate 10 seconds of my curve tracer. Okay, here is another standard SPICE program. This is actually in the release. There's this guy that sends me all these phenomenal hi-fi amplifiers that kind have part per million total harmonic distortion at 20 kilohertz. Basically, you could do atomic physics with these things, and they're all, safe operating area, protecting all that. They're just phenomenal circuits. And this guy has his own. This guy has about 4 or 5 designs that I put in the release that you can simulate yourselves. Here is a crystal. A crystal, piezoelectric crystal, is a native circuit element in QSPICE. You specify the resonant frequency, the change between the series and parallel resonances, and the sign of this specifies whether you specify the series or parallel resonance, and then the total capacitance. So these numbers would be pretty easy to measure. The total capacitance you'd get from a DC LTR meter, and then you could tickle the crystal with a signal and find the series and resonance frequencies, and it will then make a crystal model for a model for you, and you can quickly simulate crystal filters. This is because of my this is basically a linear tech style switcher. Linear tech really made a lot of money off of a current mode DC to DC converter. Okay, so they were current mode. They used true high side current sensing. They used quadratic slope compensation and frequency foldback. That was the archetypical linear technology product, and that came in all different current handling capabilities. But they made thousands of those things, thousands of different designs. And then, and this is basically that system. And I've also put in I'm going to phase lock it. A phase sensitive, a phase frequency detector is a native circuit element in QSPICE. So in this simulation, I'm going to simulate 5 milliseconds of a 100 kilohertz switcher. I'm going to phase lock it. It'll be 100 kilohertz because we're going to phase lock it to this external 100 kilohertz signal. There, it's done. It simulated 5 milliseconds in less than a third of a second of time, clock time. And here you can see it acquire phase lock. So all I got to say about that is that QSPICE is fast. I mean, there's just really no other way of explaining it. I mean, it's just really, really fast when it comes to its mixed mode simulation. Just standard SPICE stuff, it's faster than what's been out there before. But once you start having something that needs mixed mode simulation, it's really a different experience. Here is a Unitrode. I've mocked up some legacy Unitrode parts. This is actually the current version of the Unitrode part. These parts were made. These pairs were really common in the 1980s, but they kept improving them, and now they have lower quiescent current and various other objectionable behavior from these things have been removed. And so you can see this Unitrode part simulate 10 milliseconds in 1 second on the computer. Now, this model is in the release, and you can look at it. So you can enter the schematic. So this is a hierarchical design. So you can look inside the model, right-click, enter schematic. That's what's inside the model. This thing here is actually written in C, and I will do some C examples later. But you can actually look at the source code to this model. That's the piecewise linear model. And I'll type in some C and show you how to write that stuff. Here's the actual completely archetypical Unitrode part, the thing that was used for offline converters with push-pull forward converters. So this transformer is the push-pull part. This transformer is a current transformer. The switcher is actually voltage mode, but it has current protection because you're going to monitor these currents and then kick the ramp high so you terminate the cycle when you have too much current. So in this simulation, I'm going to, that's the soft start. Soft start's already done. And then I'm going to do a transient response. I'm going to go a 1 amp to 20 amp step. The blue is the current, and there's just a few milliamps of kick. It's voltage mode, it's continuous current mode, is compensated correctly. So, I mean, what are you going to do? It's going to work perfectly. Again, this is done as a hierarchical design. Like there's these boxes called 1 and 4148s and a schematic. That's just a little small signal rectifier, full wave rectifier. One is to power the IC, and then the other is to rectify the output of the current transformers. You can see whether they have too much current, no matter which leg had too much current. This is the model of the Unitroid part. Enter schematic. It's just a few analog bits, and then the whole thing is actually written in C. And that is the source code to the piecewise linear controller. I will, like I said, I will run some examples with this. I'll implement some stuff in C because it's kind of useful. There's a few parts here. This one I can't give you. Well, in principle, I could give you the source code to this because I just modeled this off the data sheet. It doesn't have any proprietary information in it. But there's a simpler part that is more interesting. I'll get into that one later. Okay, here's an example of Verilog. This part is written in Verilog. Right-click, Verilog interface, open Verilog source. So these in Verilog, there's a little IDE. If you're going to be writing in Verilog or C++, you want a little integrated development environment so you can easily navigate your source code. In Verilog, there's a strong convention that if you have a module name, the module is actually defined in a file by that module name .v. So we can look at that module, point at it, right-click, open the file, and there's that module written in Verilog. And here, and again, this, well, I actually was going to go compiling it, but that's okay. I just recompiled the thing. Open the source code. That's the source code to the other filter. And you can run this, and you can see it. It's a digital filter. It's only 8 bits, so you can see this behavior here is because you had integer rollover, and you can see the individual quantization issues because it's only an 8-bit filter. And then in C++, this example is in the release. And so enter schematic. You can look into the model, enter schematic. And this is the way the model is implemented. So we have some combinational logic, should this thing run at all? So it needs to be told, okay, you have to you have to set the enables true so it knows that it's enabled. You need to have enough input voltage. There's a high side end switch, so it needs to know that you've got boost voltage available. And if all of that's good, then you can start switching the thing. This is the actual controller, and this again is run in C++. This is a constant on-time controller, and this is not very hard to read. This is the evaluation function. Because the way you write in C++ is you draw a box, you say you want that box to be C code, and then you say make me a template. And what it's going to do is it's going to give you a function with variable names that are the voltages on that pin. So here are the voltages that are on this pin. See VIN. It knows how to it sends an array to this function, and all of this is automatically generated code. So you have a function with these variables being voltages on the pins, and you just say how output should depend on inputs. That's what you write in C. That's the method. This is a constant on-time controller, and let's run it. You see it simulates very fast. And pretty much everything is there. Let's I think it has let's try if the fault protection is there. I haven't done this in a while, so I'm not sure this will work, but let's try it. All right, so what I want to do is I want to see what happens when I short the output. All right. So I think this is gonna. Let's see whether or not I'm. Oh no, I put that in the wrong spot. I connected to the LDO. I wanted to connect it to the output. Okay, that worked. So what we have here is it did the normal startup, and then I shorted it. It went into hiccup mode, and here it did a hiccup. It said, "Oh, can I start up?" Nope, too much. I can't start up. So I turn off. I tried again. Then eventually I remove the short circuit. Then I can start again. So basically what I'm saying is that all the behavior of this part is here. You know, the boost pin current is there. Um, the switch behavior, everything is there. And you can see how fast it runs. And you can see how small and compact the model is. That's what's unique to QSPICE. All right, now we're going to get back to our question about including third-party models. Let's put some pros on it first. So this is the good news. Most models that you find on the web will simply run flawlessly with no problem. There'll be nothing you have to think about. That'll be what usually happens. If you take models from LT-SPICE, most of them will run. The stuff that's in LT-SPICE that's in open, that's publicly documented, that's not proprietary, that's not a secret to analog devices. That stuff should all run. Okay. There will be a few differences. I mentioned the Laplace. These two functions, IDT and DDT, are different in QSPICE and LT-SPICE. In LT, okay, IDT is the integral and DDT is the derivative. You can put these in a behavioral expression. Okay, you can say that this voltage is the derivative of that voltage, or it's the integral of that current, whatever. You can IDT and DDT. Well, I didn't know how to implement those when I implemented them in LT-SPICE. So they're the integral and the derivative based on up to the previous time step. They don't include the current time step. In QSPICE, these IDT and DDT, they're implemented and they are exact. They are the integral up to and including the time step that's being solved. I did not know how to put the integral of a quantity and the quantity in the same matrix and solve it all at once, which is what you have to do when you solve for for capacitors and inductors. I just didn't know how to do that in an abstract way when I implemented LT-SPICE. So in QSPICE, it has those, but they will be exact. So that would be a difference in behavior. There's an op-amp, which is a native circuit element. Maybe I should talk about this too. After I do the imported models, I'll talk about the op-amp as a native circuit element. This is going to save you a lot of trouble. This is a valuable component. Many HSPICE models will run. I've gotten parts from a couple of PDKs already running in QSPICE. That's mostly for, well, it has two uses. It has in-house use, and there's some professors that want to use QSPICE for their IC design classes. That's the good news. Now, the bad news, if you have an encrypted model, it's not going to run in QSPICE. It just will not. Doesn't matter who it's encrypted for, it won't run. LT-SPICE has these A and angstrom devices. These are not documented. Some of it has been leaked out here or there on the next place, but I don't run those. If 80, again, because QSPICE is free for everyone to use, if Analog Devices wants to standardize on QSPICE and they want me to include these, I can deal with them and it will include these devices. But short of that, I'm not interested in including them because they're an old generation of doing mixed mode simulation, which has no merit of itself besides being able to run legacy LT-SPICE models. Other than that, they don't have any value. So I'm not enthused about adding them or cloned from publicly available information. And like I said, I did get a lot of HSPICE models to run for some PDKs, some Foundry PDKs, but most of them will probably require some editing. And if there's a lot of other devices I haven't added to QSPICE that are easy for me to do if there's actually interest in doing it. You may have heard of BSIM, and you may have heard of Mextran, but there's HiSim from Hiroshima for high voltage MOSFETs. There's HiCum for RF transistors from a German, and then there's Silicon Insulator, which originally I believe is original Berkeley. So I can add those if anyone actually needs them, but right now I'm not worried about those. Okay, so now we're going to answer your question. It's easy to include third-party models. Let me park this away and have an example here. Okay, so here is my QSPICE icon. So here I have QSPICE, and here I have a third-party model. This is a triode, a vacuum tube. Let's take this model. We just drag and drop it, and it says, hey, it looks like that's a subcircuit. Do you want me to make a symbol? Go for it. And that's my model, and that's how easy it is to import a third-party model. Now, because this model was a subcircuit, it just draws a box, which isn't very interesting, but at least you can rearrange the pins. You can edit the symbol on the schematic to some extent. So cathode, plate, and grid. It's using British terms for this thing. Let's curve trace this thing. One thing about the user interface here. I said that there was no dialogue, so everything was edited in place, including the SPICE directives. But a lot of times people would want the dialogue for a SPICE directive because it gives you a form to fill out. And you don't need to know the syntax. Well, you can see underneath where I'm. So this is my cursor. This is my mouse cursor is this editor. And you can see underneath it, it's giving me the hint. So you have fewer dialogues, but more hints. B1. And when you type it in all correct, you get the little thumbs up. That doesn't mean that it's correct. It just means that it can be parsed. Okay, now let's curve trace this. It could be parsed, but it just was incorrect. I had 0 step here for this V2. And now we can look at the output transistors. You know what? So that's that part. That's curve traced. But that somehow isn't very satisfying because it sure doesn't look like a vacuum tube. Now I'm going to show you how to fix that. We can, in the schematic, you have some ability to edit symbols. You can move pins around. You can add, subtract attributes. You can do a lot, but you can't draw a picture. So let's put this symbol in the symbol editor and make it look like a picture. So here we go. File, new, symbol. All right, so this is my symbol editor. And I want to put this symbol in the symbol editor. To do that, we point at it, we type Control-C. Now, right now, the component is on the clipboard. A component is more than just a symbol. It's where to put it, rotation, name, and all that. But I'm going to paste the component into the symbol editor, and it will strip off the component and just have the symbol. Okay, good. Now I want to make this thing look like a vacuum tube. Well, the first thing we're going to do is get rid of the box. Put this up here, put this down here. We're going to give it a gloss envelope. So ellipse. We will give it a grid, line. Make that a dashed line, line type. Let's make it dashed. If we're going to draw a picture, we don't need these labels. So I said, you could all these symbols are edited in place. I could change the name, but actually what I want to do is I just don't want to show it. Now, these red dots are the justification. If I press the center red dot in the symbol editor, that would mean that it would be justified by the center of the pin, which doesn't make a lot of sense because you don't want the label right on top of the pin. So that's its way of saying it's going to be invisible. And then when you do that, it says, hey, it's going to be invisible. Is that really what you want? Because now you can't point at it if it's invisible. And say yes, then don't ask again. I'm going to make all these invisible. Okay, now let's draw a cathode and grid. Let's draw boxes for those. Okay, here we have a box. Oh, let's make it solid filled, fill color. Good. I'm typing Control C and Control V to copy this thing around. Cathodes are often drawn like that. Now we're going to draw some lines. Oh, that looks a lot more like a grid or like a vacuum tube. These are a little exaggerated long. That looks not too bad. Make this a little bigger. Good. Now let's get rid of these. Now, if in the symbol editor and you point at something, you type Control C and Control V, it's that object you've copied, and you could copy that object someplace else if you wanted to. But if you point at the background in the symbol editor and type Control C, you copy the entire symbol onto the clipboard. Let's go back to the schematic. We'll paste the symbol, and it will instance up a component. And there you are. And you know what? Let's see if the model's any good. Let's see if we can't find let's see if we can't find some output characteristics of this thing on the web. Oh, this looks good. They want $1,500 for those. Do they have a picture of the curve trace anywhere? Not there. Moon audio. Is there a picture of the curve? Do they show the output characteristics here? Let's just Google output characteristics output. Usually I can find okay, here we got something. There we are. All right, so this is going to go to 300 milliamps. So we want this to go to 300 milliamp. 360 milliamp, I should have said. And it's got 40 milliamp steps. And so,
Mike.
Yeah.
There is a question that if the distance between the grid dots, it could be configured to have like different steps there.
Okay, and are you talking about the schematic or the waveform viewer?
Oh, in the schematics.
Okay, in the schematic works like this. Everything in the schematic is an integer. It's rendered to floating point. So I have a nice floating point zoom here. Okay, but the actual data objects are stored as integers. So everything is on a grid all of the time. There's absolutely nothing you can do about it. It's just you cannot store the information that's not on a grid. It's always on a grid. For wire connections, the wire connection grids are 100. So you could have something at 0, 100, 200, 300, and the graphical objects can be within 100th of that. That lets you draw with a great deal of precision. If you make a symbol, if you can draw within 100th of a wire grid, basically there isn't anything you can't draw. It's accurate enough. So I don't know, for changing a grid size, you can show the grid on the schematic. Show grid. That'll be the wire grid. Those light dots there. I never use those, but some people like grids. I try to make as little stuff on the screen as necessary, so my eyes have as little to process as possible. So I don't use grids. I don't use grid lines in the waveform viewer. I don't use scientific notations. Just however I can, if anything I can do to remove characters, informations, or lit pixels on the screen is a benefit. That lets me look at bigger, more complicated systems. So. Let me turn off the grid. And the wire grid is fixed at 100. If you put text, it's half a grid. But if you hold down the control key, you have a finer resolution. Okay, so there's 3 modifiers. You can press down Alt, Control, and Shift. Doesn't matter which you press, but the more of them you press down, the finer grid size, the more precision you can, the finer grid size you can, because 1/100th of a wire is a very fine grid. And normally you don't want 1/100th of a grid. So here, if I press down just the control key, now Shift plus Control, now Shift and Alt, now I can move. This is almost looks like floating point. So that's how you can affect the snap that you have by holding down Shift, Control, and Alt. And what you're doing is you're going to a smaller fraction of the wire grid. Does that answer the question? I'm not hearing a response. It instills a lot of confidence that I've answered that question. Well, that's how you. Oh, I know. Control C. Let's do that in the symbol editor. View, new symbol. Let's put this here. And now let's talk about grid size. So if I move here, the grid seems fairly primitive. Hold down the Shift, it's finer. Shift, Control, and Shift also. Now I'm at final, 1/100th of a size. So that's where you get it. It's Shift, Control, and Alt. It's just the more of those keys you press down, the closer you get to the smallest grid you can use. So you don't need to remember which one does what. So that's including third-party models. If someone wants to prepare a large library, you can do that too. You can have a directory with all your symbols and libraries, and then you can drag and drop that entire directory into the symbol browser, and that's all of a sudden part of your QSPICE installation. Every time you start QSPICE, it'll open up that directory, and you can browse symbols. It will find the models in that directory. It adds to the library search paths. So that is, I think that the ability to include third-party models in QSPICE model surpasses what one generally sees in paid for SPICE simulation programs. Any more questions are importing first before I move on?
No questions, and it was answered correct, the previous one. Thanks for asking.
All right. Is he smiling? That's all I want to know.
He said thank you very much. So I'm.
That doesn't sound like a smile. He sounds like he's being a gentleman. That's the difference, Oh well. I'll just have to try harder. I want to talk now about modeling in QSPICE because they're going to end up modeling if you really exercise the program to its full extent. I had said that QSPICE allows an individual to model all the ICs for a semiconductor manufacturer. That is absolutely true. And I want to show how to include how to write a C program for that. I'll talk very briefly about, what a model is supposed to do and what you need to know to make a good model. So anyway, so what if you're going to make a model for an IC you don't have, and nobody has a model for this IC, it's got to be correct. And by that, I mean it has to steer current about the pins correctly. And I shouldn't have to say that, but you do, because there are so many op-amp models out there that don't steer, there's current that comes out the output that didn't come from any power supply. They just, the current just divinely appears on the output without having come from a power supply. So that's not right, and it messes up the operation of a lot of circuits. It's like the guy who made the model feels that Kirchhoff's law, it's just a recommendation. So anyway, you really need to steer current about the pins correctly. And if you get that right, you have a perfect model. That's the way that works. It should work for arbitrary test vectors, so that no matter how you hook up the thing, it will work. It's got to be, here's the stuff I'm going to talk a little bit more about. It's got to be robust. It's got to run fast. Because if the model causes convergence problems, or if it takes too slow to run, nobody wants to run your model. Nobody cares. It's going to be faster to design the circuit analytically, even if that's likely more error prone, or it'll ultimately just be easier to have your technician build the circuit and see if it works. Okay, it's got to be robust and fast if you want the benefit of simulation. Okay, now to do that, you need to know how SPICE works, but it is not that complicated. There's only two things you need to know. And that is, what SPICE is doing is it's solving the circuit GV equals I. It is not solving V equals IR. And from that, there's two things that you immediately know. One is that the length of time it solves GV equals I depends on the size of this matrix, which is the number of V's squared. And so the number of V's is the number of nodes. It's not the number of circuit components. So node count is more important than component count. Okay, that's one thing you should be aware of. And the other thing is that that you get from this is that you should avoid circuit elements represented as voltages. So you don't want any Thevenin or trans-Thevenin equivalent circuits, because you cannot put a voltage source in this. So that means that this is not actually quite the whole story. Every time you put a voltage source in SPICE, it makes an exception. It runs V equals IR, and then it couples the V equals I matrix, so the GV equals I, with this contraption. And the more of these exceptions you have, the more contraption you have, and you don't want any of that. You'd rather stick to V equals IR. By the way, the reason why it's GV equals I, not V equals IR, is that it comes from IC design. And a transistor is basically a transconductance, meaning a transconductance is conductance at a distance. That is, the capacitance between these two nodes depends on the voltage, the current between these two nodes depends on the voltage between these two nodes. That's conductance at a distance, and that's the way a transistor works. One of the, two of the four nodes are actually the same in a transistor, but that's why you use GV equals I, is because you can represent a transistor as a transconductance. The other thing you need to know is the basic algorithm that's used for solving nonlinear circuits. That's Newton iteration. Okay, so Newton iteration is not understood as well as it should be, especially for how simple it is. This is the way Newton iteration works. You've got this nonlinear circuit, and you get the solution to it. But you might wonder, how is that even possible? Because all of us have had courses in linear algebra. I mean, it's a university level subject. They teach you a lot of sophisticated things at university about linear algebra. We learned about rank and file and order and determinants and transpose and Hermitian and all these other nice things, inverting matrices and such not. And then, you probably learn more about linear algebra than you wanted to know. At least I did. Then, on the last day of class, the professor looks at you and he says, all this we've talked about here, this is the way it works for a linear system. If you have a nonlinear system, we're going to wish you a lot of luck with that. Point is, there is no general solution. There's no solution for the general nonlinear problem. That's exactly what you can't do. And here you have the software that solves these general nonlinear circuits with no trouble at all. What's going on? This. Point is, SPICE is not solving the general nonlinear system, not remotely. It is solving a very limited style of nonlinear system, specifically a nonlinear system where all of the IV curves are continuous in value and slope. And that is not a general nonlinear system. And that's what makes it so that you can solve it in a fairly general way. Here's the way Newton iteration works. It says, look, you've got this linear system. I've got no idea what the answer is to your circuit. But I can approximate your circuit as a Taylor series. I'll just it'll be a multi-dimensional Taylor series in each dimension, each voltage in the circuit, and then so I have it's not exactly your circuit, but it is an approximation. Now I'll solve the system with an approximation to your circuit. Okay, if the solution is the value about which you expanded the Taylor series, then you actually have the answer. You've proved you have your answer, because your approximation isn't an approximation at that point. It is exact about the point which you expanded the Taylor series in each dimension. It's, and it's closed for small perturbations, but at that point it is exact. So Newton iteration terminates in a numerical proof that has the answer. It proves that it solved the circuit. Now, if that condition isn't met, then it uses the solution of the approximation as the next point about which to expand the Taylor series and try again. Okay, that's Newton iteration. So there's a couple of things you learn from that. One is that you don't make anything more nonlinear than necessary, because it's not necessary, and it does make the circuit harder to solve. So, for example, would be you want a ideal diode in your circuit, and you've discovered that if you take the diode model parameter n and make it a very small number, the diode is goes very sharply from on to off. And say, okay, yeah, instead of making it 10, if I make it 0.1, it's real sharp. I'm going to make it 10 to the minus 6. That will be my ideal diode. That's the simplest thing, and I'll continue modeling. That's a big Class A mistake. I mean, it is very hard to solve that extreme nonlinearity, and it's more, we said it was more linear than necessary, so it's not necessary to do that. All you did was make it hard, just so you didn't have to think about how nonlinear you needed to make it. So don't do that. That's a big mistake that'll instantly give you a bunch of models that cannot be solved. The other thing you should do is make sure that every nonlinear element should be bypassed with some capacitance. Now, that is another aspect of a circuit. Every nonlinearity in every physical circuit has some capacitance. It's not zero. And that makes all the difference in the world in being able to solve your circuit in the time domain. Because if, so say you have one time point that's good. You've proved you know the answer at, time x. Now, if you want to look at time x plus delta, and you're going to do Newton iterate, you'll expand the circuit about x plus delta, but you will use the time at x as an initial iteration point at the time x plus delta. If after a few Newton iterations you don't get the answer, you realize, this just didn't work. I've taken too big of a time step. I'm going to go at x plus delta over 2. And I'll re-expand my circuit in Taylor series about the time at x over delta plus delta over 2, again using the solution at x as my initial iteration point for my Newton iteration, and try that. If that doesn't work, do x over 4, x over 8, 16, 32. Eventually, you've taken such a small, if you still can't get the solution with an itty bitty tiny time step, then it knows you have some nonlinearity which isn't bypassed with capacitance. It can't solve it, and it will give you the message time step too small. That's what it comes from. So that's all you need to know about SPICE to know how to make robust models. All right, now I want to demonstrate a couple of things first I want to start. Okay, so I showed you this practical switchboard power supply, the combinational logic in C. What I want to do now is just take it from the top and write some stuff in C, because that's really what's going to make that's really what's going to make QSPICE valuable for you. It's going to make QSPICE something that you really can't live without. Now, to write in C, the first thing you have to do is you have to save the schematic to a directory, because unlike symbols, the C code is not part of the schematic. So you have to say what directory the schematic it is. So step one is save it at someplace. File, save as, let's call it September. Okay. It's all I did is I just saved it to a directory. Now I can draw a hierarchical entry. So draw a hierarchical entry. And I don't need, it'll make up a unique name by convoluting it with the reference designator, which has to be unique. So I don't need that for this. I'll just call it September. All right. Now, this is the hierarchical entry, meaning that this symbol would be another schematic. But I don't want the symbol to be another schematic. I want it to be a DLL, which I'm going to write right now. So to do that, we have to change this hierarchical entry to be a DLL. To do that, we do right-click, show symbol properties. The icon is this little eye of the Illuminati. We come into symbol type. Do we want it to be a diode, a transconductance, an inductor, all these things. But at the bottom is a circle with a slash through it, a little Norsk O. I use that because it looks like a 0 on a computer terminal. And this now is a DLL. And now I have different right-click menus for this. Right-click, add port. I'm going to make this called input. I'll change the text justification. If I press these red dots, I change the justification. I want it justified to that dot. There, that's an input. And you have to say the port type, whether it's an input or the output. Let's say that it is an input. You can also make it the ground. You can hot deck your logic. If you're going to simulate a wall wart, the line side IC is often going up and down with hundreds of volts. But anyway, I don't need to hot deck my logic. I won't specify a ground for it. So I just say this is an input. Now you have to say the data type. If writing in C, I only ever use floating point because I would rather just do any data conversions to my C code because it's more transparent what I'm doing. It's easier for me to know what I'm doing if I just do everything floating point. If you're doing Verilog, yeah, you want to get the use the fact that QSPICE can do all the data conversions for your I/O from analog to digital. All right. Now I want an output. Control C, Control V, Control E mirrors. Let's change the name to out. And now the port type, instead of being an input, I'm going to make it an output. The data type was copied as float, so that's all good. Okay. Now I want to write the C code. Well, actually, I'll hook up a test vector first. I'll put in a sine wave. And I'll start with a simulation command. And so this is my net list. I'm going to label this net as output. So this will be what will be plotted. Okay, great. Now I'm going to write the C code. Right click. You have a C++ interface and a Verilog interface. I always use C if at all possible. And we say open the C source code. It says, I don't know what you're talking about. That file doesn't exist. Shall a new blank template be created? That's your Huckleberry. It will write the code for you. Press yes. Now it has all these options. Usually you're going to check every single one of these boxes. I'm not going to right now to make the source code as small as possible, just to make it as simple as possible. I'm just going to say OK. All right, and this is that's the C code, okay? And it will undef the names in case they conflict with a header file. I don't need to know that. There's this silly piece of glue called DLL main, which you have to define in a the function has to exist and it has to return 1 in Windows. You can use it if you want to declare a bunch of memory the first time you call this DLL main. But honestly, I never use the thing. But it does have to exist or it won't link. Okay, this is the magic. Here we have a function by the name of the module. It's got some arguments I don't have to worry about too much. But here it is what I'm looking at. It has 2 variables inside the function that are the names of the voltages. Their names are going to be, these variables will be the names of the pins, and they will be equal to the voltages on those pins. We have an input and an output, and all I have to do is write how I want the output to relate to the input. That's it. Let's just make it square. Out equals in times in. That's it. Okay. Now we right click this little symbol here, compile DLL, the little coffee grinder. The coffee grinder is the international symbol for compiling. But we can just compile and run. So let's do that. That's like F5. Okay. And that's it. It ran. See, here's the input. The blue is the input, and the green is that input squared. That's how easy it is to write in C. Draw a symbol, gives you a function. It will automatically write. It will write a program that will give you a function with the pin voltages as name variables inside that function. You just say how you want the output to equal to the to depend on the output. I don't know how to make it simpler. Okay, that's all good. Did you like that? Want to do Verilog now? Let's do Verilog. Control C, Control V. We'll give it the same vector. I have to give it a different name because this step will be the name of the module, and it'll be the name of the DLL. It has to have a different name. So now we go into right-click, Verilog interface, open Verilog source. It says, I don't know what you're talking about. You don't have one. Should I create one? Yes. And here we have a module where the pins are actual arguments to the module. And all we have to do is write some Verilog. So this one I'll cube. Right click, compile it, and it's done. Let's run the simulation. So this is the same. There's the same old other voltages. I'll look at this one. That's the thing cubed. That's how easy you could write in Verilog. All right, Verilog versus C++. There are 3 good reasons for using Verilog. One is you might be a native Verilog speaker, and that would be a good reason for using Verilog. Okay. Another reason is you might actually have the Verilog. You might be simulating something that you've programmed into an FPGA, and you've just got this Verilog. Okay. That would be a good reason for using Verilog because you already have it. You don't have to write it. And the third reason is you're designing an IC, and once you've got the Verilog, you want to synthesize silicon against your source code. So you might actually want to design the IC. Those are 3 good reasons for using Verilog. But unless you fit squarely in one of those 3 reasons, I would recommend going to C++. The problem with Verilog is that the Verilog is called that is supported in QSPICE is called synthesizable Verilog, which is a polite way of saying you can't use a delay statement. It just assumes that it's a bunch of logic which is clocked, and you've stayed within the spec of the PDK of that Verilog. You don't clock it faster than it's supposed to. So all it has to do is evaluate logic. If you're writing in C, you get to know what time it is, so you can actually run things that run on time. You can generate oscillations inside your C code that the SPICE program doesn't know anything about, doesn't have to compute those time steps. You just hypothetically consider some triangular wave, and you can exhibit macro behavior based at some much lower frequency than that lower frequency triangular wave needed. And the other reason with C++ is it tends to be it can be fantastically higher performance because those boxes that I didn't check deal with how to make a handshake between the time step control between the C++ and the Verilog. So let's get back into those boxes I didn't check. Now, the first thing I want to point out is that in this code, I said, you get this function where you have to just say how you want the output pins to depend on the input. Yeah, but that's not actually useful, because if you just wanted to do that, you could just write a B source. Sure, the B source wouldn't run as fast, but this thing doesn't have any states. You can't make a flip-flop with this because there's no stored memory. You could, in principle, put some bool bit equals. You could put some stored memory here and then access that as your bit. But the problem with that is that if you have two of these instances that call this DLL, they'll both be sharing the same bit, and you're never going to be able to figure out a circuit with a bunch of flip-flops where there's only one bit between them, all of them. So none of this is actually honestly useful. So let's make a DLL that can store bits, and let's make it so that it can actually do this time step control. So what we're going to do is we're going to throw this code away, and we're going to start over with that. Okay, so here we go to this code, right click, C++ interface. Instead of opening the source, let's create the template. And it says, oh, wait, you've got the source code. Do you really want me to throw away your source code? Do you really want me to overwrite it? Go for it. Now I'm going to check all these boxes. Okay, which you normally would do. Now you have a bigger piece of source code, and we'll go through what they do. This comment is just talking about that DLL main, which is necessary. Undefined pins, I don't need that. So this is the first issue you have to deal with. You have a structure, and you have to declare the information in the structure that you want it to that you want saved between function calls. Let me make a counter. So that means that I have a count to keep track of. But the other thing I need is I need to know. A counter has to be edge sensitive. It doesn't make any sense to me to have a counter which counts levels, because if you just hold the level, all it's going to do is just count as fast as it can. So you really have to detect the edge, and every time you get an edge, you will count. So that means that basically, you see, anytime you have an edge-sensitive flip-flop, there's actually two flip-flops in there. One flip-flop stores what the clock used to be, and then when the clock is true, when it didn't used to be clock, that's the edge. And then it writes the new level of the clock into the hidden flip-flop or the other way. It's just the way it is. All right. So now I have two structures here. There's a little bit more structure in here, and that is that it wrote these lines. Actually, it added these lines. So if you look at more of the things that are passed to the evaluation function, there's a pointer to a pointer called opaque. And what that is the simulator is giving you an address to write to, and the simulator will give you that address each and every single time. So if you want to make that address point to an allocation of its data, that's all good. And here we see it. See, if opaque isn't pointing to anything, then what it will point to will be some allocated memory, and I will null it out to 0. And then I have this pointer here that says the instance is what that pointer is pointing to. Basically, you don't have to worry about this. All you have here is, from this point on, you have a pointer of an instance pointing to this data thing here that you will get each time this thing is evaluated. All right, so let's detect the edge. First thing we have to do is all right, so here we'll have a, let's make a 7/10 of a volt logic. If the input is greater than 0.7 volts, then let's call that a true clock. All right. And the edge is when you have the clock and you didn't used to have the clock. And now we have to do the bookkeeping so that what we used to have is what the clock used to be. So that detects an edge. Okay. So the instance stores what the clock used to be. Then the next time you call this function, if you have clock, but didn't used to have the clock, that's the edge. Now, if you have an edge, then we should count. Count. Okay. And you know what? Let's print a statement that we got it. So there's this function called display, which works like printf. This is a little bit higher performance because it deals with the inter-process communication between the stimulator and the GUI. So display dot edge at t equals to make and I should so that's going to print when I got the edge and say what it made the clock equal to. And now all I have to do is do something with that clock. I mean, I could just run this thing now, but presumably I'd want the clock read back to the SPICE someplace. That's what the out will be. So out equals instance. That should work. Let's see if that compiles. It didn't like that. Okay, so that's fine. It says I have an error here. Here's the IDE. You double click on the error, and it will bring the mouse cursor to where the error is. Trouble is, it's the instance clock. Let's see if that compiles. And again, I did it again. So we go here. All right, so that runs. Or that compiles, I should say. So now let's run this thing. And so now the here we have the clock. We'll just look at the clock here. It counts up to 3. Let's, count a little higher. There we go. It's counting. Okay. That's pretty cool. Not too complicated. Didn't hurt too much. But this still isn't useful. Let me show you why. Let's zoom up on one of these edges. And look, we'll measure the rise time here. And the rise time is 27 microseconds. 27 microseconds is a long time for a rise time for a counter. So this is where we're going to get into the time step control. There are 2 functions to help you with time step control. One is called max external step size, and the other is called trunk. Max external step size adjusts the strategy, and trunk is a tactical control. Now, in life, a lot of people would spend more time thinking about strategy as more important. But in this context, you basically, the goal is to write perfect tactics. And if your tactics is perfect, you don't need the strategy. The strategy is useful for debugging. So you can tell, well, I'm probably going to need a shorter time step here until I get my trunk perfectly right. And so you can write some code. Let's do this. Right now, it's returning 1E308, which is the numerical equivalent of infinity. Let's add 1 microsecond. Okay. So now you see it took a microsecond. The time was a microsecond, but that wasn't terribly interesting. Or we could say return inst count. All right, so with this strategy is if the count is less than 10, take microsecond time steps. Otherwise, take infinity. I don't care. Let's try that. And here you can see, sure enough, here it's a very short time step. That's a microsecond. And out here, it took 29 microseconds. That was just, it was just trying to show you just enough data points to make the plot look interesting. Okay, so this is where strategy is useful. So if you're making some switcher, you might look at whether or not it's enabled. If it's enabled, take a small time step, because I haven't figured out the whole oscillator thing yet. Otherwise, take a bigger time step. That would be where the strategy is interesting. When you get your model working right, just delete this function. That will save you a little time because it won't link and it won't be called. Now let's look at the trunk. The trunk default template here, what it's doing is you can say what time resolution you want. It defaults to a nanosecond. You can make it anything you want. You want a picosecond, it'll all run fine. It'll all run just fine. And it says that if you're planning on taking a time step bigger than my tolerance, then I want you to think and maybe reduce that time step. This line is kind of magic. It's going to make a copy of your instance data. So here we have a structure of temp. It's equal to what was pointed to by instance, and then I'm going to call the evaluation function on that temp, and then all you have to do is say how to write whether or not things have changed. Okay. Now this line here of temp not equal to what's pointed, these two instances have changed. This is poetry. That's not C, because you can't do an inequality of two structures. You have to say what would be different. So you say temp count is not equal to instance. Okay, so this says the count has changed. If the count has changed, only take a nanosecond. So this thing is basically answering a hypothetical question from the SPICE simulator. It says, hey, can I take this time step? This is what I'm going to do. And you look at it and say, no, that's way too big. I need to know, my temporal tolerance here is a nanosecond. The simulator says, okay, I'm sorry, I'll take a smaller time step. Let's try that. And now we have, that doesn't look, yeah, there it is. That's here you can see the simulator doing a binary search for the right time step size, and that's your nanosecond rise time.
Mike, quick interruption. There is a question if you can show an op-amp example if you have time.
Oh, what example?
Operational amplifier, op-amp.
Oh yes, op-amp. I'm my bad. Yes, let's do that. Let's do that. Let's see. Are we done with C++? There's a couple more sentences I want to say about C++, and that is, so I've went through a lot of information here, and it's not possible to metabolize as much information I've given you. So this is how you get back to what I'm talking about. If you go to File, Open Demo, you will find an example called Practical Switch Mode Power Supply. This example is here. I've showed you a few times. It shows you how to do a very good job of writing something in C++. Enter schematic, open C source, and here you can see what this thing is doing. And we'll read through this. I'll put a prose pseudocode on top of a thing that's actually working. Here's my function with all the pin ins and outs. Declare memory if needed. And then if it's enabled, has a threshold. If it's enabled, then look at, well, were you enabled? No, I'm enabled now, but I wasn't enabled. Then you start your soft sets time and you make a note that you're enabled. So this is edge detecting the enable pin. That's what that code is doing. And then otherwise, look at how long has happened since the last transition, because you want to service minimum on times and off times, minimum on and off times. And so you look at when the last transition happened. It is basically, most of these things are going to look like a state machine. You're going to look at what state you're in, and there has this uses, excuse me. I've just enumerated states as 1 as being top switch on, -1 being bottom switch on, -2 being in hiccup mode. Otherwise, you just look at whether or not you need to. Default would actually be 0, but it's tri-stated. Anyway, if the top switch is on, has it been on for longer than the minimum on time? If so, look at the peak current. This equation is doing the peak current because I know that there's a 12 milliohm top switch, so I can infer the switch current by the voltage across the switch because I know it's on, and it's been on for a long enough period of time. If it's more than, if the peak current is more than 15 amps, start a hiccup cycle, and so there it just makes note. Okay, it puts -2 is hiccup, and it says when that transition happened. Otherwise, it's not a fault mode. You compute the on time, and the on time is simply the out divided the input times the period you want to run it at, without regard to its being regulated. It's an interesting constant on time controller. The on time is just output voltage divided by input voltage times the period of the frequency you want it to run at, but without regard to regulation. And then if you're if you start the cycle on demand, what you end up with is a constant on-time controller that's intrinsically stable, doesn't need an error amplifier, and it's as stable as a crystal oscillator. It's basically the best switch mode power supply I know of how to make. Okay, now if the instances if the state is -1, means the bottom switch is on, and the bottom switch is on, but on longer than the minimum on time, look at whether or not it's time to start a new cycle. This is part of the regulation here, though this actually supports discontinuous inductor current, even though it's synchronous rectification. At this point, the frequency will slow down. It'll be like it'll be like a burst mode, except it bursts for only one switch cycle. So it's like it's frequency folding back so that the minimum on time keeps the output in proper regulation. And then if you're in hiccup, well, is the time greater than hiccup? Then come out of hiccup and start a soft start and just wait for the demand for regulation to turn the top switch on. And there's a default catch-all. That's how that works. The truncation is the same truncation. I just look at whether the state changed, and that's the whole thing. Okay, now we're going to talk about op amps. This is the example you want to study if you want to learn to make models as well as I do. Let's talk about op amps. Okay, the symbol browser, you toggle symbol browser on and off with F2. Under behavioral, analog, op amp. Okay, so this is going to be a rail-to-rail op amp. The way a rail-to-rail op amp works is the output is complementary common source or common emitter output. So the output is very high impedance, and it's locally regulated to look more like a voltage source with a capacitance from the very output node to an internal node, and it's a Miller multiplied capacitance that's the dominant pole and tames the output gain. That's the way they're implemented. So we have to power this thing. It won't run if you don't power it. I'll run it with plus or minus 5 volt. Let's just first do a voltage follower. All right, so there's a few parameters here. There's DC gain, the gain bandwidth, slew rate. Our load is actually what load that the thing has been characterized at. Because the output impedance is infinite, the AVOL should be infinite unless you actually have an R load here. Okay, so that's in rail-to-rail outputs. A lot of people never really notice that. They specify the load resistance because if you don't say what load resistance on this number is completely meaningless. So it has a AVOL of 100K when you're loaded with the DC path of 2 kilo ohm, and here's a phase margin. Okay, let's see how this runs. So you can see this. There's the input. There's the output. Let's differentiate the output. See if how well the slew rate did. The slew rate can be something of an approximation. So it's let me get rid of this. This is slew rate 5. Supposed to be 5 meg. Yeah, it's about 5 meg. So the slew rate's about right. Let's look at the overshoot as we step the phase margin. So I'm going to step the phase margin here. Dot param. Make this bigger for you. Dot step param x list 10, 20, 30, 40, 50, 60. All right. So I'm going to do this with phase margins, all these different phase margins. Let's run this thing. And so you can see how this op amp works with different phase margins. Let's get rid of the 10 one, the 10, because it kind of puts too much clutter on the screen. So that's how you can do op amps. So this will, and the thing about this, let's look at this output current. Well, this is not a lot of, you will see it does draw current from the rails. It can have a higher quiescent current than you want because it needs internal voltages. But, I know, let's do the, all right, so there's the output current, and here you can see the supply currents. So you can see that it's the output is coming from the right supply. Basically, what's happened here is that I have a native circuit element that is a transconductance, except that it doesn't the current doesn't come from ground magically. It comes from the supply rail, so it automatically switches over from the right rail. And then I've used a few of these inside this rail-to-rail op amp to make a programmable to make an arbitrary rail-to-rail output op amp. So that's going to be very useful for you. These op amp macro models don't tend, from industry that you get from the vendors, they don't tend to be entirely useful. There is an article you could look at if you want to know the long story on that. If you go into the help file, I just pressed F1. Let's search op amp. Okay, good. I searched for op amp. Here it's describing them to some extent. And if you look at, here is a model here's an article that is documenting op amps, documenting what this part is and why it's necessary. I would, and the rail-to-rail op amp has actually been improved a lot since this article was written. But this is the prose is all correct. The implementation of the op amp has evolved quite a lot since I've written this thing. That's how I would tend to use op amps. Now you can still use third-party op amps. Let me see if I don't have one here someplace. Oh, let's try to get an op-amp model off the web. Okay, this looks like something. Here we are. So this looks like it's the official op-amp from National Now TI. Control A, Control C, Control V. Yes. Okay, good. We have to, it's just a box. We have to figure out how to do the pins here. Fortunately, it has this section. So non-inverting input is 1. Inverting input is 2. Output is 28. And 50 is going to be the negative power supply. Great. Let's try to arrange these pins to look a little bit nicer. Give it the same test vector. I'm going to run it off different power supplies. All right, so that is the 741. And this one is doing not too bad on steering the current about the rail. So this is a little bit above average op-amp model, but that's how you'd use the 741. The 741 is more quiescent current. The default device is a fairly low quiescent current here, but that is including a third-party model. Though, quite frankly, oh, and you can add noises. If the noise is documented, it's probably easier to use the rail-to-rail op-amp than a vendor model because you can add EN, IN, and ENK and INK corner frequencies. And there's also should be a common mode noise. Oh, I know, INF. Okay, so in an op amp, let me, you may or may not have, this may or may not be documented well enough. All right, so this is what the input looks like to an op amp. A lot of JFET input op amps. And what so they have a JFET input op amp has very little current noise that goes just from the JFET. But this current source often has noise. And since there's capacitance between the gate and the source, the tail current noise is conducted common mode out both inputs. And so if the impedance on both of these are the same, that common mode, like you make a classic instrumentation amplifier with 4 resistors and 1 op amp, then the impedance seen on each input is the same, and that common mode current is read out to a common mode voltage, which is rejected by the common mode rejection ratio. But the whole point of using op amps is those impedances don't have to be matched. Like here they're not. Okay, that impedance is not that impedance, and so the current noise will be this common mode current will be amplified will be turned into a normal mode signal, which is amplified by the full gain of the op amp. So that phenomenon is usually not encapsulated correctly in op amp macro models. And so if you have good enough noise data on your op amp, you're going to want to use this INF, which means current noise frequency, because this tail current noise is proportional to frequency. Did I answer the question? Come on, I just took a model off the web and poured it in QSPICE, and it ran. I'll tell you what, hold your applause to the end, all right? Just,
Okay.
So that's my 2-hour time allotment here. I very much appreciate your Insight. I appreciate it. Thanks to Insight for hosting this, putting this on. Thank you, Insight. And for the I appreciate all you guys listening to me. QSPICE is actually the only thing I do for a living. So it actually that means that any final analysis that you're interested in QSPICE, for me, is then a matter of life and death. And I appreciate that you listen to me. And I'll show you how you can contact me if you have questions in QSPICE on the Help About box. Help About. There is a contact mike.engelhardt@corvo.com. If QSPICE makes you mad, that's how you reach me.
There are 4 questions, and one of those questions is that one. How they can contact you, and how can they give you like feedback on something that they were using? So you just answered that at mike@corvo.com. But there's one question. It says, is there any special treatment that we need to do on QSPICE to get the power dissipation and temperature of the parts that you can simulate, including those?
Okay, that is actually the way it handles power dissipation is different than what I've done before. In the past, I've treated I've had a natural I had the ability to plot the power flow into a component. But the problem is that some of the power flowing into the component charges reactances instead of dissipating power. So in QSPICE, I've separated these into the actual power dissipated in the device. You can, because it can, there's a little bit of compute overhead to that. And most people, when they're trying to mock up a design, they're not immediately settling into fine points of power dissipation in the design. They're first trying to get the thing to topologically work. So by default, it is turned off. However, if you go into Edit, Preferences, this bottom line says Save Device Dissipations by default. Just check that. Now, if you put a resistor here, No, when you, I think it's, yeah, okay, good. If you hold down the control key and click on something, it will plot the dissipation. So this is the voltage on these devices. And let me add a plot pane here. Hold on the control. That's the power in the resistor. That's the power in the capacitor here, which is very low because it's only due to that 10 ohms there. You'll notice that there's a large current flowing through the capacitor, but there's very little power. It only computes true dissipation. And that, the problem with the way I've done this with passive, just looking, plotting the dissipation as the power flowing into the device. The problem with that is that a lot of times the device would put power into the rest of the circuit. Like if an integrated circuit has capacitance on the pins, and those pins discharge into the circuit, the IC is creating power. And besides being confusing, it simply isn't the quantity you want. So in QSPICE, I've gone through all the device equations of diodes and transistors and reactances and their parasitic impedances, and I actually differentiate displacement currents with voltage drops and actual real currents and voltage drops. So I actually plot the true dissipation. So that's how you do that. There's some compute overhead in doing that, so it's turned off by default. But that's how you do that. So you guys don't sound convinced. Any other questions?
Yeah, sorry, I was on mute. I was saying it's that there's another question. Is there any recommendation to modulate inductors, but with saturation current?
Oh, yeah, sure. Let's do that. So inductor saturation is a native part of QSPICE. And let's okay, so in this simulation, what I'm doing is, okay, so this is the current source. This PWL means that at time 0, I have 0 current, and at 10 seconds, I have 10 amps. The significance of this current source is that the DI/dt is 1, all right? And I can read out inductance if I assert a unit DI/dt through that inductor. Just like I can measure a resistance. If I put a unit current, if I put 1 amp through a resistor, I can read out the resistance as the voltage across the resistor with 1 amp going through it. Well, in an inductor, if I put a unit DI/dt through an inductor, I read out the inductance as the voltage across the inductor. And I'll demonstrate this here. I'll run this simulation, and we will plot. That's the output. See, it's 10 microvolts per 10 microhenry. All right, so that's how I'm reading out the inductor. Now all I have to do is add some saturation. Let's look at the help file. Point at the device, press F1, and it opens the thing up to the inductor. And I just do this at else ISAT is, because I forgot the name of the component. So that's why I opened up the help page here. ISAT is what I'm looking for. Add new inductor. ISAT equals, let's have it saturated at 5 amps. Okay, that's not real dramatic. Let's make it less. So you can see the thing saturate. Let's see what other examples we have. ISAT, stat frac. Oh, that's a specification. You can get into that, but LSAT would be the inductance that it settles to. Add new attribute, LSAT equals, is it absolute or is it relative? I have to check again. Where is LSAT? Okay, so LSAT is the percentage of pairs. Let's try 0.1. Maybe it's absolute. Okay, so it's absolute. It's not the fraction. Yeah, so that's the so that's a microhenry. Okay, good. So it starts as 100 microhenries. It ends up as 1 microhenry. And it starts losing inductance, at 0.1 amp. So that's how you do that. And there's another example I want to point out here. Under File, Open Demo, Transformer Saturation. And so QSPICE has a number of native circuit elements that aren't in SPICE that are new. And one of them that it has is a transformer. And so in this transformer, you can have any number of turns. There's symbols for 1, 2, and 3 secondaries. But if you make your own symbols, you can have as many secondaries as you want. And you put the inductor down, the symbol down. You say what the turns ratio is as a vector. Here there's only 2, so this is a 1-to-1 transformer. But it would be 1-to-1 to 3 to 5 to 6 if I had 3, secondaries. I say what the primary inductance is. It's 10 millihenry. ISAT is 35 milliamp. That's not very much, but it is what it is. And LSAT is 0.01. So it goes from 10 millihenry to 0.01 millihenry. And in this simulation, I'm going to put in a signal, and I'm going to run the simulation with 2 different values of the load resistance. It'll be 1 ohm and 1 mega ohm. So basically what I'm going to do is I'm going to run the simulation with the load attached and not attached. Let's run the simulation. And we look at the R1 is this input current. So we're looking at the input current for the load attached or not. And you see that if the load is attached, then the load pulls flux out of the inductor and it doesn't saturate and it works like a transformer. But if you remove the load, then the core saturates, even though nothing goes into the load, it shoots straight through the transformer. And the answer here is that you actually need less power if you attach the load than if you disattach if you unattach it with this poorly chosen transformer. Unless you were to solder the load to the transformer, you can't remove it. So transformer saturation, I hope you're happy with it. I think it's made to directly enter lab units for all this stuff, and I hope it works out for you. I thought you said there were 4 questions. I think we went through 3.
Yeah, the 4th one, it was related how to contact you in order to give you feedback, but you responded before I asked the question. So pretty much we covered pretty much. There's a lot of people leaving because they have other commitments at 12, and but I think we covered pretty much it. Let's wrap up, Mike, and
I hope that commitment is lunch.
Inside team, we would like to thank you again for all the help.
All right, Grotto. Y'all have an awesome day.
Thank you guys for joining us for the webinar this day. The intention is to have this more often and being thankful with Mike so we can continue working. And if you have any question, as I mentioned, if you go to qspice.com, you can get the software. It's totally free for life, and there's no phishing or anything like that. You can be installing in the computers, in the office computers as well, and there's nothing. If you need more information about what is being required, the license and all that, I have a larger document with some automotive customers ask us about it. So it is, it's being embraced in several customers right now. Oh, there was another one I forgot. The integration of the software we KiCad. I don't know you're familiar with that.
Yeah, I'm familiar with that,
Schematics.
and I use KiCad myself. I don't have an automatic way of converting a QSPICE schematic to a KiCad schematic. That is, there's all I just redrafted it in KiCad, which I think is I love the way that software works with layout and copper. It has a beautiful copper pour. I just really like it. But I even though I don't like its schematic capture, I end up having to just redraft it in KiCad. Yeah, that curve tracer was laid out in KiCad. Maybe I have a board here. Let's see. Yes, here we are. This I made with KiCad. That was that curve tracer. It's a brilliant piece of software.
Thank you very much, Mike. Are you showing something? We can close
done.
I'm done. Perfect. All right. Thanks to all. And I will be sharing the link to all the attendees. Have a great day.